Hello folks, welcome back to our discussion of integrals to find area between curves. So in the last video we talked about kind of just the basics of the most straightforward question. I have an upper boundary, I have a lower boundary, I want the area in between. And we said that as long as you have a consistent upper boundary and a consistent lower boundary, all you have to do to find the area in between is do an integral, upper boundary minus lower boundary. Maybe they gave you limits of integration, great. Maybe there's intersection points that tell you where to start and stop. Either way, it's basic upper boundary minus lower boundary every time, no matter what kind of functions you have. If they're both above, both below, a little bit of each above the x-axis, or yeah, below the x-axis, above the x-axis, doesn't matter. It's always going to be upper minus lower, and all the positives and negatives work themselves out. What I want to talk to you about in this video is the situations where it's not so straightforward. So sometimes when we look at an area, it's not terribly evident what my upper lower boundary is. Sometimes it's hard to define an upper or lower boundary. And sometimes, like in this first case we're going to talk about, there isn't a consistent upper or lower boundary because the boundary changes at some point. Now that's actually a pretty easy problem to solve. Okay, so for example, if you look at this area here in the first quadrant, so let's look at this area right here. All right, so you may see if you try to define the the boundaries for this area that along the top, my upper boundary is consistent, right? My upper boundary is g of x the whole way from 0, where this area starts, over to this intersection point where it ends. On the bottom, however, it is a different story. So if you go across the bottom boundary of this area, you may notice that for a bit, the bottom boundary is very simply the x-axis. Okay? But then right here at 1, things change. Instead of this area following along the x-axis, it starts following along this line right here. And so my boundary at one point is the x-axis, and then it switches right there. It's really nice the way my computer's keeping up with me today. Oh boy, here we go. All right, we're gonna hope my computer behaves itself. All right. It switches, right? So I'm along the x-axis, it gets to 1, and all of a sudden it switches, and now my lower boundary is f of x. Okay, this is not a problem. All we have to do, and we know we're allowed to do this, is break this area up into regions where we know we have a consistent upper and a consistent lower. Okay? If I can break it up into regions where each individual region I can define an upper and lower boundary, then I can just set up multiple integrals and add them up. And we know we're allowed to do that from way back in chapter 5. So if I want to write the area that we see here, this yellow area, I need 2 integrals. One that goes from 0 to 1. On that interval, g of x is my upper, and my lower is the x-axis. So really in here, all I need is the integral of g of x to get me this area. And then, and then I need another integral that goes from 1 out to this intersection point. I don't know, let's call it A, shall we? All right, so I need an integral that goes from 1 all the way out to A. And in this area here, it's upper boundary, which is g of x, minus a lower boundary. This time I have a lower boundary of a function, so minus f of x. And that's going to get the job done. I just have to split it into 2 separate areas. Now, you might have to split it into 3 areas or 4 areas. Sometimes we use symmetry so that we don't have to do so many integrals. We can just do one and then multiply it or something. There's all kinds of clever little things we can do when finding area. But this is one of the things we have to watch out for. If you have a boundary switch, you have to address it. If you don't, AP's going to be waiting for you. All right, let's do an example. Okay, in this problem, we have area in the first quadrant bounded by the x-axis, square root of x, and x minus 2. Okay, so let's plot these. Let's get these points up here. So if I want the square root of x, it's going to look something like that. And then the line x minus 2. Hey, look at me, I found the intersection point. Boop, boop. That's supposed to be a straight line. Okay, and the x-axis, right? So hopefully you see this. I have this like shark tooth shape where it's just like a shark fin, right? Sticking up out of the water. All right, so I need to find this shaded area right here. All right, so let's take a look at our boundaries. When you go across the top, I have a nice consistent boundary all the way across the top. Right? No problems. Same boundary from 0 out to 4. It's the same boundary all along. Across the bottom, my boundary is the x-axis, the x-axis, the x-axis. Right there at 2, the story changes, right? At 2, it switches, and my lower boundary is that line. Okay. So because I have 2 different lower boundaries, I'm going to need 2 different integrals. Okay. Anytime you have a boundary switch of any type, if the story changes, what's upper and what's lower, you got to make a new integral. So I'm going to have 2 integrals here. My first one is going to go from 0 to 2. That's going to be my upper boundary, which is root x, minus my lower boundary, which is just the x-axis. So you could put a 0 there, but you don't even really have to. And then my second one is going to go from 2 to 4. And that's going to be, oh my goodness, my upper boundary, which is root x, minus my lower boundary, which is x minus 2. Now, be really careful when you're writing these integrals. Notice I wrote the x minus 2 in parentheses. That's because this negative, you are subtracting the whole thing. That negative has to get distributed. So if you write it like this, great. If you want to distribute that negative and just write root x minus x plus 2, you can do that. But what you don't want to do is write this without the parentheses, because then you have not distributed the negative, and that is officially an incorrect answer. Okay. Now, we could do these integrals by hand, but there's no reason to. We're just working on finding areas here. Again, if this is a calculator portion of the test, you can just use your calculator to do those integrals. You do not need to do them by hand. All right, so that is an example of a boundary switch. Okay. The other thing that I want to talk to you about is something called integrating on y. Some people really love this. Some people have trouble seeing it and avoid it at all costs. I have found that there are very few situations that come up for us on the AP where we're forced to integrate on y. Sometimes the problem they give us is a lot easier to solve if we integrate on y. You can avoid a boundary change, or you know, maybe the integral's a little easier, but it's not, I've not seen anywhere you are forced to integrate on y. But I will show it to you anyway, because you never know. All right, so if I wanted to find the area between this blue curve and this red curve, all right, let's call them f of x and g of x just because it makes them easier to talk about. All right, if I say to you, I want you to find this area right here. Do you see how in this particular situation, instead of having a clear upper and lower boundary, you have kind of a left and right boundary? So, in other words, instead of saying, okay, I want to integrate from 1 to 4, and here's my upper minus lower, your upper and lower are straight lines. It's the starting and ending points that are varied. When you see a situation like this, when you see a left and right boundaries instead of above and below boundaries, that is a big flag that, whoa, this is probably going to be easier to do if you integrated on y. And what we mean by integrating on y is rewriting your integral so that your functions are in terms of y instead of x. So in other words, instead of drawing your rectangles, because remember, all an integral is we're taking areas of rectangles, right? And we're adding up an infinite number of rectangles, right? When you draw your rectangles vertically like this, the width of them is dx, the height of them is f of x, right? That's why if we want the area under a curve, we just do f of x dx. This is the area of one rectangle, and then we integrate to add them all up. Here, instead of vertical rectangles, what we're going to do is we're going to draw our rectangles this way. We're going to draw horizontal rectangles. Now, why on earth would I want to do that, other than it looks really nice? Okay. Well, look what happens. Down here, I've got short rectangles. Up here, I'm going to have a longer rectangle. And I can still write an equation for the area of these rectangles. And now I have a clear boundary on both sides, and I have a very clear starting point when y equals 1, and a very clear ending point when y equals 2. Okay. So if I want to write the equation for the area of these rectangles so that I can add them all up, I just need to think about their dimensions, right? So their heights are now, instead of being a dx because it's a width, now the differential is the height. So instead of this being a dx, the height is a dy. Now, I can figure out this distance by simply subtracting g of x and f of x. Okay? In other words, instead of doing upper y value minus lower y value, we're going to be doing upper x value, or I like to call it the outer one, minus the inner one. So sometimes, I kid you not, it helps people to literally just go like this. So it's upper, so then once you turn your head 90 degrees, or your paper, if you're so inclined, then instead of looking like a left-right boundary, it looks like an up and down boundary, and sometimes that helps people see it. But that's all we're going to do here, is we're going to take this x value minus this x value to get the height, or in this case, the width of our rectangles, and then the height of them is going to be dy. So when I write my integral, it's still going to be an upper boundary minus lower boundary. Big X value minus little x value. But those will be written in terms of y, right? Because they'll be x equals. My height is going to be dy, and so when I integrate, my limits of integration will also be y. It's going to get me the area in the same way that it would if I used vertical rectangles. It's just that for some problems, it's easier to use y's. Right? Let's look at an example. Oh, it's the same problem. I wonder if there's a different way to do it. Let's see, shall we? So I have my square root. And I have my x minus 2. Let's see if I can draw a better line this time. Not too shabby, Britton. Okay, now, here's what I want you to notice. Same area as before, except now, if I look at it, instead of looking at it as a top-bottom boundary, if I look at it as a left boundary, right boundary, right, outer minus inner, so from the y-axis, where x is 0, right, at this, right here, x is 0, and then x gets bigger from there, right? If I look at it as a left and right boundary, on the left-hand side, my boundary is the square root of x every time. On the right-hand side, my boundary is x minus 2 every time. So in this case, I can set up an integral to do the same area as we just did. I said I don't need a boundary switch this time. If I set it up in terms of y, no boundary switch. Okay, so let's check this out. I can say, you know what, I really hate doing boundary switches. Instead of doing a boundary switch, I'm just going to do my rectangle horizontally to avoid said boundary switch. So every single rectangle is going to have a height of dy. My first rectangle is going to be down here on the x-axis. That's where my first rectangle is going to be. And instead of putting them next to each other, I'm just going to stack them, right? Stack all my rectangles until I'll get all the way up here. I'm going to have little tiny rectangles. Right? The closer I get to this little point on my shark fin, the smaller my rectangles will be. So if I want to add up all these rectangles, I know my first rectangle is going to be down here at 0. And my last rectangle is going to be up here at 2. Notice my limits of integration are on y. because as soon as I drew my rectangle horizontally, I determined that. As soon as you draw your rectangle horizontally, your tiny, infinitely small measurement is a y. Everything's in terms of y. This expression will be in terms of y, and there will be a dy sitting out here. Okay. So if I want to write the equation for one of these rectangles, I just need this dimension. I need to know this length. The height is dy. Well, this length is a consequence of what your boundaries are, right? In this case, my outer boundary is x minus 2. Well, what's the x value right there? The x value right there is y plus 2. I literally just solved that equation for x. So right here, my x value is equal to y plus 2. Over here, this is y equals square root of x, so my x value right here is y squared. So if I want the length of this rectangle, I just need my bigger x value, which would be the one that's out here, minus my smaller x value, which would be the one in here. So my equation for the length of this rectangle, or the width of it, is going to be y plus 2 minus y squared. That integral is going to get you the same answer as the last one we did, where we did a boundary switch. Now, I know what some of you are saying right now. I'll do 10 boundary switches before I draw a horizontal rectangle again. And I get you. I see how you feel. Right? But you do have to be able to set it up or minimally recognize it, because they could easily throw you like a multiple choice and say, which one of these integrals gives this area? And you look over and all the integrals are written in terms of y. Okay? Usually the ones they give you can be done both ways. And there are some questions on the Pearson assignment where they actually give you the same problem and they ask you to set it up both ways. But some people really, really hate horizontal rectangles. Like, it throws them off, and that's fine. Usually you can avoid them, but you do have to be able to do them, right? So do get some practice with them. Nope, oh, don't look at that. Okay, let's just make a quick sketch. All right, y is x cubed, so that's going to look like something like that. Oh boy. You know what? I'm going to do better. So I'm telling myself I am. Okay. X cubed. I tried. Okay, and then notice this one, and this is usually another hint that you've got something that you might want to think about what variable you're integrating on. Notice this one is defined in terms of y, this is defined in terms of x. Okay, so if you're not sure what this looks like, you could solve it for y, right? If you add 2 to both sides, what you get here is a square root function shifted back 2, and it's the positive root and the negative root. But again, you may recognize what that is. It's just a sideways parabola. Right? So look what I have. If this was y equals x squared minus 2, you'd say, oh, that's a parabola shifted down 2. Well, it's x equals y squared. So it's a sideways parabola shifted back 2. All right. So here's that parabola. Okay, so let's identify our area first of all. I've got this area right here. Now look, let's see. If we integrate with vertical rectangles, we integrate up and down, you will notice that from here, which is my leftmost point, over to here, which is our rightmost point, my upper boundary is consistent. It's this positive root x plus 2. My lower boundary, though, not so much. It's negative root x plus 2 up till this point right here, and then it switches to the x cubed. And I can do that. I can make a boundary switch. No big deal. But why would I when I could draw a horizontal rectangle? So look, if we do a horizontal rectangle, from on the left, I have a clear boundary the whole time. It's this parabola. On the right, I have a clear boundary the whole time. It's this cubic. No boundary switch. Okay. So let's set it up like that. I know I'm going to have dy. And I know my limits of integration are going to have to be on y. So I need my intersection points. I need this point right here. We'll call them A and B for now. I need the width of this rectangle. All right, so look, I need the x value right here minus the x value right here. That's all I need. Right? This parabola, it was already solved for x. The x value right here is y squared minus 2. Over here, they gave me y equals x cubed, but I can get that into an x value real quick. X has to equal the cube root of y. So if I want the width of this rectangle, it's going to be the bigger x value, which is cube root of y, minus the smaller x value, which is x squared minus, or y squared minus 2. So y squared, I'm going to distribute my negative, plus 2. Okay, now to get intersection points here, we need to set these two equal to each other, right? So I need to take the cube root of y and set it equal to y squared minus 2. Now this is something you're going to have to do on your calculator, right? You're not going to just find those. So they would either give you those points generically and just call them like A and B, or it would be a calculator problem where you would use it to find your intersection points. Okay? If it's a calculator problem, probably you're going to have funky intersection points. Piece of advice, and I know I've said this before, but I'm going to say it again because it's super, super important. If you do have to calculate intersection points like you have to do here, what you never, ever, 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 ever want to do is do that calculation, write down a rounded answer, and then use that rounded answer to do another calculation. That's a no-no. If you do that, you are risking your final answer not being accurate to 3 decimal places. What AP expects is that all of your calculations are using the full exact number and you round at the very end, right? You don't want to do calculations with rounded numbers. So here, if you're going to do a second calc intersect and get these points as decimals, you need to store them in your calculator, right? Which is also why it helps to call them letters, right? Call them A and B, so that after you do your second calc intersect, you have that number up on your screen, you hit store and call it A. Now, here's the thing. I need you to know this. Pay attention. You listening? When you store a number, it stores the X value every time. And if somebody can figure out how to make it store the Y value, I would love to hear it. I have been unsuccessful at that as of now. However, it's pretty easy to find the Y value, right? So when you do the intersection point, you find the X value, cube it, and get the Y value, right? And then on the other one, you already have it, right? But you've got to go find, it's always going to store the X value. And if the Y, what you want is the Y value for your integral, you've got to go calculate it from the X value. And you definitely don't want to calculate it using a rounded number. So store that X value and use it to find your Y value. And then store that Y value so that when you go to do your integral and it asks you for your limits of integration, you can put in like A and B, and it uses your full stored values. Now, on your paper, you might just write 2 decimal places or 3 decimal places, but you know that you're using the full decimal when you do your calculation. And in the end, your answer then won't be a rounded answer. You'll have a nice exact answer, and then you can round it. Okay, super, super important. All right. I think that's enough of my voice for now. We will talk more about this, and I will see you soon.